say we have a point A in space, and we know that the origin, say, is over here. We can draw a position vector from the origin to point A. So this is vector OA, and I'm going to just call it vector little a like this. So say I wanted a line that went through point A and also went through some other point R. I know that 2 points define a line, and I know that if I have the coordinates of A and R, I can write the equation of the line that goes through them. And the form that you usually write the equation of a line in is called Cartesian form. Today we're going to learn the vector equation of a line. We're going to see how to break that up into parametric equations of the line, and how to convert those into Cartesian form, which is the familiar form of a line. So I can also write a position vector from the origin to point R, vector OR, and I'm going to call that vector little r. If I know the direction that my line's pointing in, or I can say that my line itself is parallel to some vector b, but obviously it's not the same magnitude because it's a line, so its magnitude is infinite. Alright, so again, r is the position vector from the origin to any point on the line, and I'm just naming this other point r. So I can use what I know about vectors to write an equation for this position vector r. I know that vector OA is vector OA plus vector AR is equal to this position vector r. OA plus AR is equal to OR, and OR is my position vector r. OA is this little vector A, is this position vector A from the origin to point A, and vector AR, I don't know how long it is, but I know what direction it's going. And because I know that vector AR is parallel to vector B, I know that vector AR has to be a scalar multiple of vector B. So instead of AR, I'm going to write a scalar multiple of vector b, and the scalar I'm going to use is t. So t is a scalar. It's just some real number. So t is an element of the set of all real numbers. Alright, so this is the vector form of the equation of a line. The position vector from the origin to any point on the line is equal to the position vector from the origin to some other point on the line, this is usually a reference point or a given point, plus some scalar parameter times the direction vector b. Vector equation of a line. If I think about the components of the vectors r, a, and b, if it's in 2 dimensions, then r would have an x component and also a y component. The same with A and the same with B. So if I write this out like this, I could say R, or the x and y coordinates of point R, is equal to the x component of vector A, which I'll call A sub x, and then this is the y component of vector A sub y, plus t, my scalar parameter, times the x component of the direction vector b and x component of direction vector y. If I write my vector equation of a line in component form, I can split it into 2 equations, my x equation and my y equation. If I was in 3 dimensions, I would have, of course, a z down here. So I would just have 3 components. So I can split this up into 3 equations where I'd have x is equal to the x component of A plus t times the x component of B, and so on. And these are my parametric equations of the line. So again, these are the parametric equations of a line. Okay, I can convert my parametric equations into a Cartesian equation, which is the standard equation of a line that you're used to looking at and working with, by eliminating the parameter. So I'm just going to do this in 2 dimensions, just for simplicity's sake. Actually, no, I'll do it in 3. So I want to solve each of my parametric equations for my parameter t. Then I can set them equal to each other. All right, so the first one, if I solve x equals the x component of a plus t times the x component of b for t, I'm going to get x minus, to stay out of, thank you, a sub x is equal to t times b sub x. So if I want to solve for t, I just divide by b, like so. And I could do the same for the other equations. It would be y minus a sub y over b sub y is equal to t. I changed my mind. I'm just going to do this in 2 dimensions. So for a line in 2 dimensions, I can get the Cartesian form of the equation by setting t equal to t, and I'll have x minus a sub x over b sub x is equal to y minus a sub y over b sub y. If I rearrange this equation, I can get it into the standard form, which is some coefficient a x plus some coefficient b y equals c, right? Or I could put it into y equals mx plus b, which is a different b than this. So I'm going to make it a funny b. All right, and these are the Cartesian form of the equations of a line.